Right, let's draw the analogy or the comparisons between electric fields and gravitational fields. All right, starting maybe on the left-hand side with our gravitational fields, the formula for force, inverse square law, G m1 m2, that's going to be 1 over r squared. The formula for electric force, Coulomb's law, Q, let's use small q's because I was using small q's before, Q1 Q2 over 4 pi E naught R squared. So both inverse square laws. If we think about the nature of the forces, in the case of mass, there's only one type of mass, and we get an attractive force. In the case of charges, we can have positive or negative charges, so two types of charges, and so we have two types of forces, attractive or repulsive. Let's define our field strengths. Basic definition, the general sort of term that defines gravitational field strength, little g, is going to be force per unit mass. Electric field strength, force per unit, but you must remember to say positive in there as well. Force per unit positive charge, that takes into account the fact that we've got the two possibilities here of positive or negative charges. For a radial field, then, that formula for gravitational field strength becomes G m over r squared, and the formula for electric field strength becomes Q over 4 pi E naught r squared. So once again, inverse square laws at work, measured in newtons per kilogram and newtons per coulomb. EP, and the EP really is a step towards getting at potential, but EP in a gravitational field, negative G M1 M2 over R, right, where we take EP equals 0 at infinity. EP in the electrical situation plus or minus Q1 Q2 over 4 pi E naught R. So both of these are inverse laws at work. In the case of the electrical, it could be plus or minus depending upon whether we are close to a positive charge, which would, or to a negative charge. So whether the force is going to be an attractive or a repulsive force. All right, based on the potential energy arguments, we can then come up with a formula for potential. Gravitational potential, negative G m over R. Electrical potential, V. General definition, remember, work done per unit charge. In this particular case then, plus or minus Q over 4 pi E naught R. Positive potential if you're near a positive charge. A negative potential if you're near a negative charge. Okay, so those are probably the parallels, but there is still that distinction between the fact that you've got a symmetry, if you like, in this situation where you're dealing with both positive and negative charges, whereas the gravitational, where you've only got an attractive force acting, is sort of like half the story. And that's what forces us into this negative sign in formulas like that, where we've got the attractive force, whereas over here we've got positive or negative depending upon whether we've got an attractive force or a repulsive force at work.